Hello everyone. Here in this video, we would like to derive an equation for the frequency of a stationary wave in a stretched string, right? So let me start by saying what is the least mode of creating a stationary wave in a stretched string. So imagine a stretched string fixed between two rigid supports like this. Let the length of this stretched string is equal to L, and I have disturbed it at the middle. As I told you in the previous class, previous video, wherever you disturb it, there the displacement is maximum. So an antinode is formed like this. It goes to this end, and then as it's an obstacle, the wave comes back, and this is called a segment. This is how a stationary wave is formed. It's very clear that this point is called as node. This point is called node where the displacement is minimum. This point is called antinode where the displacement is maximum. If you notice, this is only a half of a wave. If a complete wave means a crest and trough also has to be there, but trough is not there. So the distance between node and node is equal to half the wavelength because it's half the wave. So it's very clear that the entire length of a stretched string is equal to lambda by 2. That implies lambda equal to 2L. We have also derived expression for the velocity of a stretched string as root of tension by linear density. But we know V equal to n lambda. We have already proved that. That implies frequency n is equal to V by lambda. V is root of tension by linear density. By lambda means 1 by 2L. This is the least vibration that it can make. I can call it like N1. And this is called something like fundamental frequency of a stretched string. Or fundamental, this vibration, this kind of a vibration is called fundamental mode of vibration. It has a minimum frequency of this much, 1 by 2L into root of tension by linear density. This fundamental mode of vibration or a fundamental harmonic this is also called as first harmonic. We call this also as a first harmonic. That is, this is the harmonic that it can make. It cannot make any vibration or a segment less than this. That's why this is called as first harmonic. Anyway, you can express it in an exaggerated way by saying it as zero overtone. Zero overtone. See, overtone is a exaggerated way of saying it. But as you have exaggerated, its value shall not change. That's why I call it like a zero overtone. So harmonic is a normal way of saying if harmonic is first, when you exaggerated the way of saying, the number has to be reduced to 0. So you need to know that the overtone number is always 1 less than that of the harmonic. So that's the first harmonic. Now it can have other kind of a harmonic, say for example, second harmonic. It's obvious that you want to call it like second harmonic in another way. You call it like it as first overtone. As overtone is an exaggerated way, number is reduced from 2 to 1. So overtone number is always 1 less than that of harmonic. So how is that vibration happens? Let us consider a stretched string. Don't pluck it at the middle, but pluck it at 1 by 4th of the length at the middle of this place, right? So you have disturbed it at a distance that is equal to L by 4. At the point of plucking, as I told you, I will get a maximum displacement, that is amplitude. So the wave goes like this. Now as it got an obstacle, it comes back like this. So you can clearly see there are two segments formed here. This is node. This is also a node. This is also a node. This is antinode and this is antinode. So in second harmonic, you can see there are 3 nodes, 2 antinodes. Whereas in first harmonic, there are 2 nodes and only 1 antinode. So be careful in understanding that antinode number is always 1 less than that of the nodes number. So the entire length of the string L behaves as if like only one wave. This is the crest of the wave, this is the trough of the wave. The distance between them, node and node, as I told you earlier, is lambda by 2. So between these two, lambda by 2. Between this node and node, another lambda by 2. So the total length is summation of that 2 lambda by 2s are one wave, that is lambda. Then the frequency of a stretched string is n is equal to v by lambda. Lambda is L itself, 1 by L. V is root of tension by linear density, mu. But here the first one is in the format of 1 by 2L. So I will divide this equation with 2 and multiply with 2. 2 by 2L of root of tension, 1 by L or 2 by 2L, both are same. So N2 is equal to 2 times of 1 by 2L into root of tension by linear density. But that 1 by 2L root of tension by linear density is nothing but N1. So the second harmonic frequency is 2 times of the first harmonic frequency. That's the point that I want you to get. That is second harmonic. Like that, it can have many harmonics. For your convenience, I will draw the third harmonic. I'll call that as either third harmonic, or you can call that as second overtone. So here, to get this second harmonic, I have plucked it at L by 4. Let us now pluck it at L by 6, not even at the half of it, but you will pluck it at L by 6. So what happens in that case? There is a wave comes, crest, trough, again crest. This is how it goes. As it goes an obstacle here, it comes back this way, this way. So there are 3 segments formed. This is called a segment. How many number of the nodes? This is a node, 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 and node. Nodes are 4 then. How many number of antinodes? 1, 2, 3. Antinodes are 3. So in a stationary wave, antinodes is always one number less than that of a node. This entire length of the stretched string is shared as between node and node 1 lambda by 2. Again this node and node 1 lambda by 2. This node and node lambda by 2. So the total length is lambda by 2 plus lambda by 2 plus lambda by 2, 3 lambda by 2. So in this case, lambda equal to 2L by 3. That implies frequency N3 is V by lambda. V is root of tension by linear density. Lambda is the denominator, therefore it shall be reversed. 3 by 2L. So if you notice carefully, this is the original frequency of the first case itself. So N3 is equal to 3 times of N1. So the kind of a conclusion we can say in the case of a stretched string, the ratios of frequencies is 1 is to 2 is to 3. This is N, this is 2N, this is 3N. Therefore, they are having a ratio of 1 is to 2 is to 3 and so on. If you vibrate it in this way, like only one segment, that is called first harmonic. If it is vibrated in 2 segments, that's called second harmonic or zero overtone. If it is vibrated in third segment, 3 segments, it is called third harmonic or second overtone, and so on. This can happen further, right? This is the ratio of fundamental frequencies of a stretched string, right? From this you can get the, so you can say in general, say for example, for n number of segments, any number of segments, for p number of segments, I can write n in general as p by 2l into root of tension by linear density, where p is number of segments. Here, number of segments is 1, so in this case, p becomes 1. In the second case, p becomes 2, like we have derived. In the third case, P becomes 3 like we have derived. So this is a general formula. From this, we can also get the laws of stretched strings that we will discuss as and when it required, right? That's it. Thank you for watching.